Alright, so let us cover today the second basic lemma, which is very similar in spirit to the one that we did yesterday. So this is called the Angle Bisector theorem, and what we did yesterday was the perpendicular bisector theorem. So how it goes is like this: you take some angle and draw an angle bisector of this angle. Now, what you must understand is that this construction, this particular construction is a very popular one, and all of us know how to do this accurately by compass. So, if these two angles are equal, and if I take up a point on the angle bisector, in that case, the distance of the point P from this line and the second line, the distance, the perpendicular distance, the shortest distance of that point from these two lines are equal. So you can see that how similar it sounds to the theorem that we did yesterday. And once again, the converse is true, and both these theorems, the theorem and the converse, are used quite a lot in most of our geometric arguments. So what is the converse? So let's just state it. If you take some angle and you happen to find a point P, you happen to locate a point P where you find that the perpendicular distance of this point from this line L1 is equal to the perpendicular distance of this point P from this line L2, and you find that these two are equal, then you can be assured that you happen to be on the line which is the angle bisector of angle A. In other words, these two angles will be equal. So this is the statement of the angle bisector theorem and the converse. Now once again, we urge you to write down a proof for this, and it's a simple exercise in congruence of triangles, so this should not take you much time. Now what I shall now proceed in this video, just like yesterday, is that the angle bisector theorem helps us to locate an interesting point of the triangle, which is the center of the incircle. So let's go ahead and understand what this is. The incircle of a triangle. So just like the circumcircle of the triangle is unique, and there is a single circle which is the circumcircle of the triangle, of an arbitrary triangle. So once again, I take an arbitrary triangle, and here's what we shall do. Let us try to draw the angle bisector of A, of B, and do the same thing for A. Then the point of intersection happens to be the incenter of the circle of this triangle. Now we shall find it extremely easy to prove by using the theorem that we just stated. So this point, because it is on the angle bisector of B, from what we just learned, the perpendicular distance from this line and the perpendicular distance from this line is the same. So let's just call it R in anticipation of the fact that this shall be the in radius. Now you can see that because this point I also lies on the perpendicular bisector of angle A, so let's just mark it just to make sure this is the angle bisectors of A and B respectively. Now since I lies on the angle bisector of A, by the converse of the angle bisector theorem, what we should understand is this perpendicular distance to this line and the perpendicular distance to this line are equal. And what that would mean is, since we've already called this a small r, this will also be r. And you can see that if I keep a compass here at I and draw a circle, I might get something like this. And this is what we mean by the incircle of this triangle. Now, because of the perpendicularity or the 90 degrees, what we quickly see is that these lines, which are the sides of the triangle, are actually tangents to the circle. And this is a nice incircle whose radius is r. One also quickly notes that since these two r's are same, I lies on the perpendicular bisector of C, and therefore we can make a nice statement, and we should just write it down here. Angle bisectors, like the perpendicular bisectors yesterday, are concurrent. So this is very neat and clear from here that the angle bisectors are concurrent. They meet at I, which is the incenter of the triangle, and these three triangle sides are actually tangent to this circle. And now we also ask the question, do we get a nice formula for the in radius? So let us now work on this, because it gives a very nice configuration. So at this point, I'd just like to remind you that you will find most of what we do in the classic book Geometry Revisited, and once again I invite you to get hold of this book immediately and have a look at it. A couple of small things I would like to point out. I just want you to note that this point, which is the extension of the angle bisector, does not, these 2 points are, it's very obvious, but I just want to highlight that these 2 points really are not the same. Okay, so let's start looking at this configuration. Many things are very easy and extremely nice, extremely well known. So first of all, note that these tangent segments are equal. So this is one of the things that we studied very early, that tangent segments are equal, and you can prove it if you haven't done this before. Now once you note down that the tangent segments are equal, let us try to write down, let's call this tangent segment as x, which means that this tangent segment is also x. So let me just clean up the board a bit, because we're going to write this down very easily, and this tangent segment is also x. Similarly, this tangent segment, let's call it y, and therefore this is also y, because tangent segments are equal. And this tangent segment, let us call this z, and again these two are equal. Now in this configuration, let us write down a few obvious things from the diagram. You can see here that 2x plus 2y plus 2z is actually equal to the perimeter of the triangle. Now this immediately gives us x plus y plus z is equal to the perimeter divided by 2, and this is called the semi-perimeter, and we use the standard symbol S for the semi-perimeter. So x plus y plus z is equal to the semi-perimeter, and this you must have already met when you must have studied Heron's formula for the area of a triangle. Now this is our first important equation, x plus y plus z, as with x and y and z as shown in the diagram, is actually equal to the semi-perimeter. Now we make one neat observation here, which is this side is actually equal to A, and you can see from here that A is equal to Z plus 1. Now, if you substitute this here, y plus z as A, you immediately get that x is equal to s minus A, and this is indeed extremely nice and neat. So let us write this down immediately here. X is equal to s minus A, x is equal to s minus A. And quickly you can notice by symmetry then in this picture, y will be equal to s minus c, and y will be equal to s minus c, and here in this picture z will be equal to s minus b, and z will be equal to s minus b. So we got so much interesting formulae already on the board, and just by a neat diagram. Now the last thing we could do here from here is to make use of all the information that is already there on the picture and write down, if possible, a formula, our first formula for the in radius. So here's the first formula for the in radius. I would ask you to look into this particular triangle and notice that this particular triangle has got a right angle here. So there is a right angle here, and one immediately notices that tan of A by 2, I'm talking about this angle, tan of that angle is equal to the opposite side divided by the adjacent side. Now the adjacent side is s minus A, and you can see here that we have a formula, our first formula for the in radius. And now, like yesterday, by symmetry we can rattle off several other formulas. Tan B by 2 will then be equal to R over S minus B, and tan of C by 2 will be equal to R over S minus C. So here is our first formula for the in radius, and this is a very neat set of symmetric formulae. But we are not done with this. This is going to give us, this picture is going to give us one more very simple formula in 2 lines. So I think I want to get to that now, and I hope that this picture is reasonably clear, not too cluttered up. Now just to make some space and not draw the diagram all over again, I shall just erase this. And now watch here. You just need to make one simple observation before we get on to another neat formula. Notice these 3 triangles. So you have one triangle like this, another triangle like this, and another triangle like this. It is very easy to find the area of each of the triangles that I've just drawn. So the total area of the triangle ABC, is the area of the first triangle that I've drawn here or indicated, half base into the height. So it's going to be half, what is the base here? What is the base here? It is C. So half C into height, and the height happens to be the in radius. Now similarly for this particular triangle, it's going to be plus half A into R plus half B into R. And I just simplify this and I get half A plus B plus C into R, and you already have used half of the perimeter as S. So this is equal to S into R. And what a neat formula we have. So just write it here. it says that the area of the triangle is equal to SR, and here is as neat as a formula as one can imagine for the end radius. And now let's combine it with the formula that we did down yesterday. Now I could just tell you what the formula is, or let's just do it all over again in a couple of minutes. We started off by saying that the area of a triangle is equal to half AB into sine C. So this is a quick reminder of a very well-known formula. And then of course we wrote C by sine C is equal to 2R. So this is the other formula that we have, and we combine these two formulas to get the area is equal to half AB C by 2R. Now what this is saying is that the area of the triangle is equal to ABC over 4R, and now we will just plug this into this formula that we just got, and we get SR is equal to ABC over 4R, and maybe I should just leave it at this. So here's another beautiful formula which we get so easily, and with that I think this has also been a quick revision of the formulas we did yesterday, and indeed I would say that this is a good place to stop the angle bisector theorem. So I shall try and look up one or two more very interesting configurations like this, all from the book Geometry Revisited, and I shall present this over the next couple of videos, and I hope that you'll also be drawn towards the book. There's so much geometry that you can learn, and you can see that this is indeed extremely elegant and very beautiful geometry and very easy to pick up. All the best.